So those are our practice problems that I asked you to start with. Let's talk about rounding 36,000 to one sig fig. Okay, this is not a question of how many sig figs there are. We're given a number. What we have is a problem. The first problem is to round 36,000 down to one sig fig. When you round a number off, you do not want to lose the value of the number, the magnitude. Magnitude means size. So for example, let's say you loan somebody $36,000. You're a banker. You loan somebody $36,000 so they can go buy a car. Now in your mind, as you're just checking your daily transactions, just ballpark it. You're not going to round that off to $6,000. You loan $36,000. You're not going to say, oh yeah, Joe owes me owes the bank $6,000, which is one sig fig. If you cut off the wrong digit, you completely change the value of that number. All right, that is not the right way to round the number off. You do not round from the large side, or you will change the value of the number. You're getting rid of the most important digit on there, the highest digit. So when you round numbers off, you always cut off from the small end. So when you say somebody owes $36,000, you in your mind, just as you're doing a rough estimate, you may be thinking, okay, I got to remember Joe owes the bank $40,000. That's how you do it, $40,000. Now we're instinctive about that with money. Somebody owes you $9.95. You call them up and say, hey, don't forget to bring my 10 tonight. When I see you, bring me my 10 tonight. You wouldn't round it down to 95 cents. Hey, don't forget to bring me my 95 cents. They're like, yeah, right. And that's what you remember? Okay. So the point is, when you round, you always chop off on the small end and you got to retain the magnitude of the number originally. Magnitude means size. So if that number is in the 10,000th place, which it is, when you're done rounding, there better still be a number in the 10,000th place. So we need to have one sig fig. Remember, decimal point absent come from the Atlantic. There are two sig figs there. Now this process is not about eliminating zeros from the size. It's about eliminating zeros from the assessment of the exactness of the number. The zeros are still important for the size of the number to retain its value. So what we see is we've got two sig figs, but the problem is to write this to one sig fig. So we're going to chop off the 6. We're going to keep the 3. Well, we're not going to keep the 3. We're going to keep approximately 3 because we follow the same rounding rules that we learned in elementary school. If the number you cut off is 5 or greater, then you bump up that number. So we write a 4, and now that 4 needs to be in the 10,000th place. So we're going to use placeholding zeros to make that happen. So we put a 0, 0, 0, 0, and that 4 is in the 10,000th place. The value of 36,000 to one sig fig is approximately 40,000. So do this. Round that number to 2 sig figs. All right, 2 sig figs. Boom. We're going to keep these two. So we go 4, 4, 0, 0, 0. Right? I don't know if I told you guys this analogy, but at some point I told some classes about this hypothetical imaginary chicken farm where you have eggs that are rolling down these little, from the chicken coops. They're rolling down onto a conveyor belt, and the conveyor belt can weigh the eggs and make a rough assessment of how many eggs are being produced. In a chicken farm, the hens are all in these little coops, and they lay eggs every morning, and they just lay them right on the wire, and they roll down onto a conveyor belt, and the conveyor belt takes them to be sorted into small, medium, and large. They actually have little holes in the conveyor belt that lets the small ones pass through first, and then the medium ones, and then the large ones are left over. Well, this conveyor belt that I'm talking about, it can make a determination based on the average weight of eggs, how many eggs are being produced. But it can't distinguish between 1 egg and 2 eggs. It's not that sensitive. It can distinguish between 10, 20, 0, right? So in other words, this conveyor belt is sensitive to the 10's place, not the 1's place. So if there's 7 eggs on this conveyor belt, it registers as 10, which sounds like a big error. But if you're making, if you're boxing, a couple hundred eggs a day, being off by 3 roughly, it's not that big of a deal. There's 3 eggs are going to break over the course of the day anyway. So, so if you've got 7 eggs on the conveyor belt, which is not going to happen, that's too few, it would register as 10. If you had 17 eggs on the conveyor belt, it would register as 20. If you had 12 eggs on the conveyor belt, it would register as 10. Thank you for the real life people. 12 eggs on that conveyor belt would register as 10. We got this conveyor belt that's sensitive to the 10's place. It cannot distinguish between 1 egg or 2 eggs, but it can distinguish between 10, 20, 0. All right. So, in a machine like that, if you have 100 eggs, if the machine tells you that you have 100 eggs, this 0 is only a placeholder. It was not measured. If my conveyor belt egg machine tells me that 100 eggs are produced before noon, I can only rely on that digit and that digit. Those digits have value. In 1's place, 0 is only a placeholder. In my egg machine, the 1's place will always be a 0. It can never be a number other than 0 because my machine cannot detect individual eggs reliably. It can only detect 10 or more eggs. and it detects them in groups of tens, by the tens. Okay, so that we say that this number has two significant figures. How in the world do you write the number 100 so that you can communicate to somebody that that zero has significance, whereas that zero doesn't? That's the point of problem 2. That's the point of this problem, to illustrate that. So let me show you. Watch this, guys. 100 times 10 to the 0 equals what?
100.
What does that equal to? In purple, what does that equal to?
100.
100. How many sig figs on the left?
1.
You see a decimal point present?
Oh, that'll be 2, right?
Decimal point present come from the Pacific. Stop at the first non-zero digit. 1 is a non-zero digit. Count it and all remaining places. That is 2 sig figs. The correct way to write 100 to show that that zero is significant is in scientific notation. You cannot write it in standard notation to show that the middle zero is significant. Now, depending who your professor is in college, they may tell you, or maybe Dr. Rivera for physics, if you take him next year, he may tell you that you can write it like this. Some people will tell you to put an underscore under the zero, but that is not universally accepted. It depends. You might not be able to do that. You might be able to do that at University of Florida, but not at Florida State. I don't know. It depends on your professor. This is a hack. It is not necessarily universally accepted. This is the Bible. That is the correct way to do it. This is the beginning step of writing in scientific notation. Since scientific notation is defined as a number that is written as a product of a power of 10, the first thing that I do when I see that I need to show a zero is significant, I know that I'm going to be putting the number in scientific notation, so I go ahead and write it times 10 to the 0, because that's the first step for putting a standard number into scientific notation. 10 to the 0 equals 1. I do not change the number by doing that. I then count how many times I move the decimal so that there's one non-zero digit to the left of the decimal place. That's what the count 2 there is. I have moved the decimal twice. I then, because I've made this number smaller by moving the decimal 2 times, I have to make the power of 10 larger. So I take that 2 and I add it to the 0, and I get 10 to the 2. By increasing the power of 10 here and decreasing the power of 10 there, I still have the same value, but I can now write it as a decimal number that shows the significance of that 0. Let's try it on the second problem. Maybe if I was at UF, I could do it like that, right? But I'm not, and I don't know that for sure anyway. So here's what I do. Times 10 to the 0. Then I go 1, 2, 3, 4, 5. I decrease the value of the front part of that number by 5 powers of 10, but I'm not allowed to do that without balancing it, so I increase the backside of that number by 5 powers of 10. I now get 1.800 times 10 to the 5th. That is the only universally acceptable way to write $180,000 with 4, or 180,000 with 4 sig figs. I'm looking for 2 answers. 1 sig fig. We're going to chop it off here, and it's going to be 2 times 10 to the what? 1, 2, 3, 4, 5, 6, 7. Oh, that's 1 sig fig. What about 5 sig figs? Well, let's start over again. Let's go up here. That's the number, right? So we go ahead and multiply by 10 to the 0. I'll walk you through it. We need 5 sig figs. So watch what I'm going to do. I need 1, 2, 3, 4, 5. I need those 5 digits, so I'm going to cut those off. But first of all, let's see where that decimal is going to go. 1, 2, 3, 4, 5, 6, 7. 2.0500 times 10 to the 7. 1, 2, 3, 4, 5. Boom, I'm done. Okay, so you want to know about 5 sig figs. Okay, so from the studio audience, we had a question about how you get 5 sig figs. So let's do that again. 20,500,000. And I asked for 5 sig figs. You always keep the large numbers. Count all 5. I need to keep those 5. Now, I can't distinguish between that 0 and this 0, that one having significance and that one not having significance. So I know now I must write in scientific notation. So I'm going to go ahead and rewrite this number times 10 to the 0. By doing so, I have not changed the value of the number. I'm now going to move my decimal place. 1, 2, 3, 4, 5, 6, 7 powers of 10 to the left, which makes my number smaller. Now I'm going to go ahead and write all those zeros again. Let's see. 5, 1, 2, 3, 4, 5, 2, 3, 4, 5 again. So because I've made the left side of the number 7 powers of 10 smaller, I have to make the right side of the number 7 powers of 10 bigger to balance it out. So that becomes 0 plus 7, or 10 to the 7. That's scientific notation. Everybody should be comfortable with it. If you're not, get a calculator, which you should have, punch the number in, and force it into scientific notation mode, and you'll get that number. That will not be the right answer, but now you're ready to then look at those digits that you want to keep. 1, 2, 3, 4, 5, cut those off. That's all. You just count from the larger side towards the smaller side, the number of sig figs that you need to keep. Anybody have a question online?
Do you always have to put the decimal after the first digit?
That is the definition of scientific notation. Scientific notation is a method of writing a number as a product of a power of 10 such that there is only one digit to the left of the decimal place. Now, there are exceptions to that. When you are trying to compare two numbers in scientific notation that have different powers of 10, and you feel it is important to show them side by side with the same power of 10, you can sometimes break that rule to make a point. People do it in scientific journals. But typically, in my class, because I'm teaching you the right way to do it first. By the way, if you don't know what art is learning how to do something the right way and then skillfully breaking the rules that describe the right way so that you pleasantly surprise people. That's the art of telling jokes. It's the art of painting a picture. It's the art of doing almost anything. You learn the right way to do something, and then you skillfully break those rules when you're master of those rules, and you will pleasantly surprise people. They say, oh, did you see what he did there? I did. That was cool. All right, so learn the right way to do it first, and then you can break the rules.
Mr.
All right.
Bagel,
Yes?
I have a question. So you can't put like 2.05 times 10 to the 7th? Or you have to put like all the zeros?
You can put 2.05 times 10 to the 7, and the size is correct, but the exactness is not correct, and you will lose points. This is a question about exactness.
Okay, thank you.
If you take out those sections, those zeros.
Okay, so the correct answer is, I thought it was clear. That is the correct answer all the way at the bottom of the screen. That is how you write the answer with 5 sig figs. And everybody got how to do it with 1 sig fig, right? That was easy. You don't even need scientific notation for 1 sig fig. Really. For 1 sig fig, you could have just wrote this. What is that? 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. That's standard notation. That's the right answer in standard notation for 1 sig fig, or you could have written 2 times 10 to the 7, which is easy. Number 3, what's the area of a wall? This has to do with last class lesson. All right, so you got this wall that is 16.2 meters long by 3.54 meters tall. I want to know what the area is.
Mr. Bagel,
Yeah?
do we round this answer?
So that is exactly what I'm teaching you how to do, or that's what I taught you how to do. How do you round? You will never need to ask me again. I'm telling you, going forward, that whenever you do a calculation, it is your responsibility to round your answers the way I've taught you to do. So that is the point. .54 times 16.2 is 57.348. Meter times meter is meters squared. This is the wrong answer. It would be correct in math class, but this is not math class. This is chemistry, and we're learning how to keep track of exactness through calculations. So what we have to do, it's called the weakest link rule. The answer can only be as strong as the weakest link. The answer can only be as exact as the most inexact number in the problem. So we're going to evaluate. Decimal point present come from the Pacific. Now let me stop here. The Atlantic Pacific rule for when zeros are significant and when they're just placeholders is about zeros. Every other digit, 1 through 9, are always significant. The Atlantic Pacific rule is to evaluate when a zero is significant and when it's only a placeholder. My point here is not to reteach you that. My point here is to show you you don't need that rule because there's no zeros. There's no zeros. So I don't need to ask decimal point present or absent because there's no zeros to make a decision about. All digits, 1 through 9, are always significant. So this number has 3 sig figs. The 3 significant, the 5 significant, the 4 significant. There are no zeros to make a decision about. So 3 sig figs. Here we have 16.2 meters. There are no zeros. I don't need to ask Pacific or Atlantic, so or present or absent. So 1, 2, 3 digits, so, and they're all non-zero, so they're all significant, 3 sig figs. So my answer can only have the lower of those two numbers. Well, those two numbers are the same, 3, 3, 3. So there is no lower number, but there's no higher number either. That means I can only have 3 sig figs in my answer. So again, I start on the large side of the number and I count 3. 1, 2, 3. Those are the digits I'm going to keep. I cut off everything else. I keep the units, but I cut off the other numbers. The correct answer to this calculation then is 57. Hold on, that was bad. The correct answer is 57.3 meters squared. Let's try the Scotch tape problem. We have a piece of Scotch tape. Most people don't think of it as being three-dimensional. It's so thin, but it does have a very slight thickness to it. So I want to know what the volume of this piece of Scotch tape is if it is 19.05 millimeters in width, if it is 62.5 millimeters in length, and if the thickness of it, that's supposed to be a bracket, if the thickness of it is 0.062 millimeters. What's the volume? 62.5 millimeters times 19.05 millimeters times, here's the kicker. This number only has 2 sig figs. So let's evaluate this. It's a mathematical problem. I mean, it's a multiplication problem. We're going to look at sig figs. 3 sig figs, 4 sig figs, 2 sig figs. Okay? No zeros, so all digits there count. Uh-oh, there's a 0. Now, if you read the rules of sig figs, that 0 is significant because it's called a sandwich 0. It's in between 2 significant numbers, so it has to be significant. But you don't need to memorize them. You say decimal point present, come from the Pacific, stop at the first non-zero. 1905, boom, 4 sig figs. This number has zeros. I'm going to write it on the board so the people on this virtual world can see this. Decimal point present, come from the Pacific. Stop at the first non-zero, count it in all remaining places, 2 sig figs. For the value, 62.5 times 19.05 times 0.062 equals. In math class, the correct answer would have been, Miss Jones, I got 73.81875. Good job, Tommy. But that's not the right answer in chemistry. All right, millimeters cubed. M, 3 times. We only get 2 sig figs, so we're going to chop it off. Remember, we go from the big side, chop that off. The correct answer, as Veronica said, is 74 millimeters cubed. So we got this building 1 and building 2. Building 1 is this, building 2 is that. We want to know the total volume of 2 buildings. So building 1 is 24.75 by 8.25, but it's a long one. So we got this one building that looks like this. So there's building 1. And next to it, side by side, is building 2 that is taller than that. Okay, that's building 2, and that's 48.125. And what we want to know is what's the total volume. Now don't get all freaked out. You take the volume of building 1, you take the volume of building 2, you add them together. So we have from here to here 48, we have 12.5, and we have 18.35 in width. Okay, so the volume of building 1, I'm going to subscript it like that. V1 is equal to 8.2. Volume 1 is 24.75 times 8.25 times 115.45. And of course, that's meters cubed. These are meters times meters times meters. So I'm just going to put meters cubed at the end. I've already done the math on meters. Meter times meter times meters, meters cubed. Building 2, I'll put down here. Volume 2 is equal to 18.35. Look, times meters in my head and get meters cubed. So the top box is 23573.44688 meters cubed. Now that is the wrong answer because I'm not rounding it off yet. V2 is equal to, okay, so I've got both of my unrounded volumes. The problem is, do you know how to calculate a volume? That is expected. The problem here is, did you learn how to round off correctly? So let's evaluate. 3 sig figs, 4 sig figs, and 5 sig figs. All right, I got to tell you something. This is the point of this problem. When you calculate volume or something that requires the same multiplication, or multiplication division, maybe we're doing density, and we had to do mass over volume. So we weigh something, mass. We measure length, width, height, we calculate volume, and then we divide mass over volume to get density. You'll notice that division, mass divided by volume, and volume, length times width times height, they're the same operation. They have the same rounding rule, count sig figs. That was in last lecture. When you multiply or divide, the answer can have no more significant figures than the least amount in the problem. You do not round every time you hit the multiplication sign or division sign or equal sign. You only round once at the end of all of those similar operations, multiplication, division. Same rule, don't round off until the end. Here's the point of this problem. Write this down if you need to. If you have to change rounding rules, then you have to round off before you do. In other words, I'll say it again. If you have to change rounding rules, then you have to round off before you change rounding rules. If you have to change rounding rules, because you're changing operations, if you have to change rounding rules, then you have to round off before you change rounding rules. So if you're not changing rounding rules, you don't round off until the very end. That means if you have a series of multiplication and divisions, you just round off one time at the end. If you have a series of addition and subtraction, you just round off one time at the end. But if you're going from multiplication to addition, or if you're going from subtraction to division or subtraction to multiplication, that means you do the first rule, round it off, and then move to the second rule, round it off again. So here, because we're doing volume, and then we're going to do a VT, the total volume is volume 1 plus volume 2. That means we have to calculate the volume by multiplication, separated by addition. So we're going to round, you're rounding by sig fig rules, and then you add and you round by DP, decimal places. When you add or subtract, the answer can only have the number of decimal places as the least amount in the problem. All right, so we're going to round this off. 3, 4, 5 sig figs. So that means we go with the lower number of sig figs, 3. I'm counting them off from the big side. So that number is 23,573. I'm going to round that number up to 23,600. So V1, I'll write it here. V1 rounded off to 3 sig figs is 23,600. Let's copy over here. 23,600. That's only the first building. Now we got to look at the second building. We've got the volume. Let's take and evaluate for sig figs. We have 4 sig figs, we have 3 sig figs, and we have 5 sig figs. So once again, 3. 1, 2, 3. Uh-oh, there's that 0. Then we have to go to scientific notation here. I'm going to go, let's see, 1, 2, 3, 4. So that is 1.10 times 10 to the 4th meters cubed. Now we got to add those two. So V2 is 1.10 times 10 to the 4th. Now, if it makes you feel better, what? Wait, is that it? Okay, guys. Add it up, round it off to the decimal place. Notice there are no decimal places. There are no decimal places. So you just add those two and you're done. VT is that what's that. Bye, guys.